MOS transistor short channel effects. When the length of the transistor is below 1 micrometer, we observe non-idealities with the devices. The three short channel effects are: one is drain to bulk and source to bulk diodes and drain induced barrier lowering. Second is mobility degradation. Third is velocity saturation. Drain to bulk diode and source to bulk diode and drain induced barrier lowering. We know that when VGS voltage is greater than the threshold voltage, the channel under the gate is inverted. When the channel is very narrow, that is, the length of the channel is lesser than 1 micrometer, it means the channel is very narrow. So the part of the channel is already occupied by the depletion region of the source to bulk and the drain to bulk diodes. So this is bulk is a P substrate, this is N plus. When we have P and N, there is a diode formed. This is P region and N region. So you can see we have a diode here. And we have a diode in this direction also because of N plus and P. So this is P, N, this is P, this is N. So when the part of the work is already done by the depletion region of the source to bulk and the drain to bulk PN junction. Hence the part of the work is already done, so the threshold voltage is less when the length of the channel is small. So as length decreases, the threshold voltage decreases. We know that when the diode is reverse biased and we increase the voltage, the depletion region increases. So when the drain to source voltage, that is the drain to source voltage, increases, it means the N region is more positive and the P region is more negative, that is in reverse bias, and the depletion region increases. So the part of the channel is here. In this case, the larger part of the channel is occupied by the depletion region, and hence the threshold voltage value decreases. So the more part of channel is already depleted, and hence the threshold voltage is reduced. This is called as drain induced barrier lowering. So the threshold voltage is a function of length. Smaller length, smaller threshold voltage, and it is a function of UDS. Larger the value of UDS, the smaller is the threshold voltage, and it is also the function of source to bulk, that is the body effect which is discussed. Mobility degradation because of the vertical electric field. When the channel is short and when the thickness of the oxide is also small, the electric field generated by the gate to source voltage, which is greater than the threshold voltage, is very high. Because of this following equations, we know that electric field is voltage divided by D. So when the thickness is small, that D is small, the electric field is very high. High electric field and a small channel results in electrons being very close to each other, and frequent hitting of electrons happens, and this leads to reduction of mobility of electrons. The channel becomes shallow and scattering of electrons occurs, and hence the mobility of the electrons reduces. This is called as mobility degradation because of vertical field. Next is velocity saturation due to lateral field. It is lateral electric field, which is going from the drain to source because of the drain to source voltage. For long channels, we assume that the drift velocity V is proportional to the electric field, and V equals to mobility times electric field. However, in short channels, as we observe here, for electric fields up to 1 volt per micrometer, we see the linear behavior according to this equation. However, for large values of electric field, the velocity, the drift velocity, becomes saturated, that is, becomes constant. Hence, the saturation current equation ID becomes linear, and it is not a quadratic as shown in the equation, that ID is proportional to UGS minus UT.